Hello student. So let us start our discussion. So in previous lecture we have discussed common bus system. So in that topic we have discussed that how we can connect multiple register to via common bus to memory and other registers, and how CPU will execute operations. So in this topic or in this video we will try to discuss what is computer instruction. So we will try to learn that how instruction is formulated, or how computer understand the instruction. So let us start our discussion. So today's topic our current topic is computer instruction. Okay, so as we know that size of accumulator is 16-bit. Okay, so out of this 16-bit, 12-bit will be used for address. Now how many bits left? Only 4. So this 4-bit will be used to specify opcode and addressing mode. Clear with this? Okay, so this is how instruction is formulated. So right now we will not focus on this 12-bit. Okay, we will try to focus on this 4-bit. So let us start our discussion. For opcode we will require, or we will have 3-bit, and for addressing mode we will have 1-bit. So computer will figure out the type of operation from this. Okay, so if we have total 3-bit, okay, then how many total combinations are possible? We will have total 8 possible combination. Okay, so let me write down those combination. So 0 0 0 0 0 0 1 0 1 0 0 1 1, then 1 0 0 1 0 1 1 1 0 1 1 1. Now this 3-bit we have considered. So if we combine these 3 with the addressing, then we will have total 4. And if we divide, if we try to generate all the possible combination using 4-bit, then it will be again same 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Yes, what is difference here? It will be all 0. Here it will be 1. Here it will be 0, and here it will be 1. Clear with this? Okay, so if we try to divide this, then it will be divided into 3 groups. Group 1, this is group 1, this is group 2, and this is group 3. Clear with this? So using this we can say 4-bit computer will figure out that which operation is to be performed. Now if pattern of those 4-bit it belongs to group 1, okay, then it will be considered as a memory reference instruction. Clear? Then it will be considered as a memory reference instruction, right? Means this group, it will belongs to this group. If 0 1 1, then it is known as register reference, and if it is all 1 and all 1, then it is IO instruction. Clear with this? Okay, so this is how computer will divide any instruction into 3 groups. Okay, so and based on this binary pattern, it will figure out that which operation is to be performed. Now next thing, how computer will know that whether it has to deal with the memory or not. Okay, so first computer will check this opcode, and if that opcode belongs to that group, then accordingly it will treat. So let me tell you, let me be very clear. In memory reference instruction, computer will treat bit number 0 to bit number 11 as a address of memory, while in this both case computer will treat this 12 bit as an opcode, means operation. It will specify operation. Same as register reference instruction, computer will use this bit number 0 to 11 for opcode. Clear? So in case of memory reference, computer will treat this 12 bit as an address, while in this register reference instruction and in IO reference instruction, computer will treat as an opcode. Now let me discuss various instruction. So let us start with the memory reference instruction. Now how many bits are there in instruction register? There are 16 bits, so we will represent 16 bit in form of hexadecimal. Okay, so let us assume this is some binary number, so we will write it in form of hexadecimal. We will convert this represent to this represent to this represent to this, and last 4 bit represent last digit. Okay, so I hope you are clear with this. So in case of memory reference instruction, okay, if you try to recall the table which we have drawn here, okay, then for memory reference, what will be the value? It will be 0, then 12 bit address, then 1, 12 bit address, then 2, 12 bit address, 3, 12 bit address, 4, 12 bit address, 5, 12 bit address, 6, 12 bit address, then 7, 12 bit address, 8, 12 bit, 9, 12 bit, 10, 12 bit. Okay, now instead of 10, what we have to write here? A 12 bit, B 12 bit, C 12 bit, D 12 bit, E 12 bit, and F 12 bit. Okay, so if value of this 3 bit is 0, then it represents the AND operation. If value of this bit it is 001, okay, it can be 0 or it can be 1, means 1 and 9, so it represents the add instruction. Similarly 0 1 0, 0 and 1 combined, so it will represent the LDA. Then next instruction will be STA, then next BUN, then BSA, and at last ISZ. Yes, here what AND will do, this instruction will do, it will go to the memory location which is specified using this 12 bit, and then it will retrieve the content of that memory location and perform the logical AND operation with the accumulator and store result into accumulator. What add will do? Simply whatever location we have specified using those 12 bit, it will go to memory location, retrieve the content, and it will add the content with the accumulator and store result into accumulator. So similarly LDA, what LDA will do? LDA will load accumulator, means whatever value is specified on a particular memory location, so those 16-bit value will be loaded into accumulator. What STA will do, whatever location we have specified using 12-bit, the content of accumulator will be stored on that location. Okay, so in LDA we are loading into accumulator, while in case of STA we will store the content of accumulator into memory. What is next? BUN. BUN means branch unconditionally. So if you want to jump from one location or from one instruction to a particular instruction, or from one memory location to another location, then this instruction will be used. So it will jump to the location which is specified by this 12-bit. BSA, branch and save return address. So difference between branch unconditional and branch and save return address is, here we will not store the return address, while in case of branch and save return address we will store the return address. Next, ISZ, increment a memory word and skip the next instruction if it is 0. So what this will do, it will go to the memory location which is specified by this 12-bit, then it will retrieve that operand, then it will increment that operand, and if the value of operand is 0, then it will skip the instruction. So how we can skip the instruction? We can increment the program counter by 1. Why? Because program counter will point towards the next instruction that is to be executed. So if we want to skip the next instruction, then we will increment the program counter. It will skip the next instruction. Clear with this? Okay. Now let's have a look at the register reference instruction. So in register reference instruction, 4 most significant bits are fixed. Okay, so those are 7. So we have to deal with only remaining 12. So in that case it will be like, let's say here it is 0 0 and here 8, so 0 0 0 1. This is binary, this is hexadecimal, this is hexadecimal. So this represent the CLA. CLA means clear accumulator. Next is 0 1 000, then 0 0. This represent the clear extended accumulator. Then next is 0 0 1 0. Okay, you just remember this is binary and this is hexadecimal. So it represents the complement accumulator, means it will simply complement the accumulator value. means wherever there is 0 it will be converted to 1, and wherever there is 1 it will be converted to 0. Okay, next is 0 0 0 1. Okay, then 0 and 0. Again, this is binary, this both are hexadecimal, so this will represent into, it will be represented into complement extended bit of accumulator. Then next is all will be 0, and this 0 will be 1 0 0 0. Okay, and this will be, so here this is hexadecimal, this is hexadecimal, while this is binary. So this represent the circular shift right, okay, through accumulator plus AC, not only accumulator. Next is 0, then 0 1 0 0, and this will be 0. So this is known as CLE, circular left accumulator plus extended accumulator. Next is 0, then 0 0 1 0, and this will be 0. So it will result into INC. INC means increment value of accumulator. Next is 0 0 0 0 1 and 0. So this is the SPA. Skip the next instruction if accumulator is positive. Skip the next instruction if accumulator is positive. Okay, let me write few more here. Next will be 0, this is hexadecimal, again hexadecimal, then 1 0 0 0. Okay, so this is known as SNA. Skip the next instruction if accumulator is negative. Next instruction is 0 hexadecimal 0 hexadecimal, then 0 1 0 0. So this is SZA. Means skip next instruction if accumulator is 0, and then 0 0 0 0 1 0. Okay, this is hexadecimal, this is hexadecimal, this is binary. So it will result into SZD. SZD means skip the next instruction if extended bit of accumulator is 0. Means if carry is 0, then in simple word we can say that if carry is 0, then there will be skipping of next instruction. We will increment the program counter. And last one 0 0 0 0 0 1. So this is halt. Halt means it will stop the execution, so it will tell computer to complete the to hold the execution. Okay, so if you will now, if you try to convert this into actual value, then it will be like 7 8 0 0 7 4 0 0, then 7 2 0 0 7 1 0 0 7 0 8 0 7 0 4 0 7 0 2 0 7 0 1 0. Here it will be 7 0 0 8 7 0 0 4 7 0 0 2 7 0 0 1. Now why we are using this 12 bit as an opcode? Why? Because these instructions are register reference instruction. So by default operand will be inside accumulator. So whatever operation we will perform in register reference instruction, there will be no need to access the memory. While in case of memory reference instruction, this 12 bit we will use for the address. Same thing will happen in case of IO operation or IO instruction. So if we consider this as a F, then 4 value will be like 1 0 0 0 and then 0 0. This both are hexadecimal, this is hexadecimal and this is binary. Similarly F 0 1 0 0 0 0. next F001000, last one 000100. Okay, so 4 instruction and remaining two F0, both are hexadecimal, and here it will be 100 and 0, and last instruction from this category 01000. Okay, so this is if we write in hexadecimal format, then this is F800, then F400, F200, F100, then here it will be F080 and F040. Meaning of this is INP, means whenever this instruction will be executed, accumulator will try to read the input register and it will transfer the 8 bit from input register into accumulator. Next is F400. Meaning of this is out. Out means it will send the 8 bit to output register, and from output register it will be sent to output device. Next is F200. So F200 means SKI. So here if input flag is set, then program counter will be incremented, or you can say next instruction will be skipped. And here SKO, next instruction is skip if output flag is set. So skip the next instruction if output flag is set. So it will skip the next instruction, or it will increment the program counter if value of output flag is 1. Last one is I on, last second, and last one is I off. So this both are basically related to interrupt. So if we enable this, or if we will execute this instruction, then any other external process can interrupt, or it may oppose the execution of currently executing instruction. And if we execute the last instruction, that is I off, then it will disable the interrupt. So while we are executing a particular instruction, or you can say sequence, then no other instruction can be executed. So in upcoming videos we will discuss what is input flag, what is output flag, what is interrupt. So we are going to discuss interrupt cycle as well as input output cycle. So this is how computer manage the instruction. Okay, now if you want to say that a computer is complete, okay, then how we can say it? So it is also known as completeness of instruction set. So first of all, what is instruction set? In each computer there will be some fixed set of instruction which are specifically designed for individual system. Okay, so for Intel processor there will be separate instruction set instruction, then for AMD processor there will be separate instruction, then for Sun Microsystem means Sun Microsystem processor will have a different instruction set likewise. So instruction set is specific to hardware. Now next thing, that how we can say that instruction set is complete. So if instruction set contain 4 type of instruction, okay, then we can say that it is complete instruction set. So what is the first instruction? First instruction is data manipulation. So if instruction set is having data manipulation instruction like CLA, CLE, complement, then circular, and then add, and okay, then we can say it is required part. What is next instruction? data transfer instruction. Okay, so instruction which will help us to transfer data from CPU to memory or from memory to CPU, like load is there, store is there. In stack based organization we are having push, pop, okay, then exchange. So those kind of instructions are also required in instruction set, so it will allow us to deal with the memory. Next is program control. Now, what is program control instruction? The instruction which will help us to manage the execution of program. So, for example, let me tell you here, branch unconditional, which will help us to jump from one location to another location, or it will help us to jump to a specific instruction. Then BSA, branch and save return address. So this is also program control instruction. This is also program control instruction. Then skip in input flag, output flag. So these are also program control, you can say, instruction. These are also program control instruction, and this is also, so the instruction which help us to manage the execution of program, it is known as program control instruction. And last category, that is IO instruction. Okay, so the instruction which will help us to perform input operation and output operation. Okay, why? Because without input and output, there is no use of computer. Okay, we have to provide some input, so computer will manipulate it, and after manipulation computer will give us output. So if we want to say that the instruction set is complete instruction set, then it must satisfy this requirement, okay, or it must contain these four type of instruction, which are data manipulation, data transfer, program control, and IO instruction. Okay, so in this lecture we will keep up to this. Thank you.